Thanks. Let's begin. Dear Heavenly Father, again, Lord, we thank you that you love us like you do. We thank you that you're an awesome God, and we thank you for your grace and mercy to us each and every day. Pray that you be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. All right, so go ahead and collect your homework if you want to pass it over. Get that out of the way. So if you've been following, excuse me, if you've been following what I've done in here, I've not followed the book lately, right? What did I do? Let's kind of recap what happened in here. I went to section 12.8 if you want to think about the book, right? I started by defining for you guys what on earth a power series is. I said a power series, basically it's a function defined pointwise by a series formula, right? And then I went on to describe to you how if we wanted to, say, reproduce a function that was given through some other means with a power series, then we would do so with the formulas which we know as Taylor's theorem or Taylor's formula. And if you follow the book, sections 12.6 through 12.9, he goes kind of a different route, right? Start with, he has a section 12.6 where he talks about Taylor polynomials and he talks about Lagrange's formula for the remainder, and then he kind of goes from there, right? So I'm gonna try to go back and pick up some of the pieces and worry a little bit more about the theory that I have been not worrying too much about just yet. So let me start with that. So section 12.6, we have Taylor's theorem. This is theorem 12.6.1. So what I'm going to try to explain to you guys today is a few subtle, really subtle ideas. I've tried to show you the advantage of calculating as we do here, but now I need to go back and address some fundamental issues. So f of x is equal to f of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared plus plus the nth derivative at 0 over n factorial times x to the n, and then plus Rn of x. So what does he say? He says this is assuming what's the assumption here? What do we assume about f? F has n plus 1 continuous derivatives on an open interval I that contains 0, and so here he assumes what? Assuming f is n plus 1 times continuously differentiable. On I that contains 0. And then this is if x is an element of I, then we get this. But there's more, right? With what? Rn of x equals to what? Rn of x is equal to 1 over n factorial, the integral from 0 to x of the n plus 1th derivative at t times x minus t to the n power dt. And this Rn of x is called the remainder. All right, this is Taylor's theorem in all of its glory. I'm not going to prove this, but I'll sketch the proof. How would you prove this? I mean, here's a sketch, just like your homework. Which one am I talking about? Which homework problem did you do that was the n equals 2 case of this? Do you remember? let's see here. What section was that in? That was back we got to use the Wayback Machine here. I think chapter 8, right? Integration by parts section, remember? In the integration by parts section, there was this weird homework problem that I assigned you guys. You guys asked me about it because it was weird. But I explained how to do it right over there, if I remember right. I'm talking about, in particular, problems number 78 of section 8.2. So the point basically there, what do we do is basically you just start with the integral. In this case, you'd start with this integral. And then what do? You just integrate by parts until you beat it into submission, and out pops the formula. The actual details are on page 604 of your text, and you can look at them if you want. Now, what's interesting is it's not this so much. It's the theorem that follows. The next theorem, 12.6.2, which is Lagrange's form of the remainder, I guess formula for the remainder. What's that say? Lagrange's formula for the remainder says that, in fact, the Rn of x above can be written as what? It can actually be written as the n plus 1th derivative evaluated at c divided by n plus 1 factorial, right? Times x to the n plus 1 for some c. And so here's a picture. If this is 0 and this is x, c is here. On the other hand, if this is 0 and this is x, then the c is over here somewhere, okay? He wants to allow x to either be to the left or to the right of 0. That's the setup here. All right. And, an immediate corollary would be that well, let's see here. If you can bound the n plus 1th derivative, then you can bound the size of the remainder, right? And that's the result that you actually use to do the estimation error problems in 12.6, right? So if we have that the n plus 1th derivative of x is less than or equal to m on the interval under consideration, then Rn, the absolute value of R of n of x, is less than or equal to m. And, the x should be what? Yeah. Well, no. I guess I just leave it absolute value of x plus xn plus 1 divided by n plus 1 factorial. All we're doing is taking the absolute value of this and using the fact that if the n plus 1th derivative is at most m, for each x and I, then it follows that we have that the absolute value of the remainder is less than or equal to m times the absolute value of x to the n plus 1 over n plus 1 factorial for each x and I. There's nothing especially surprising about what I just said. That's just kind of common sense, let's say. Now, terminology, right? There are two separate issues of convergence I'm going to talk about today. Whoa. All right, so the first one that comes to us is that if Rn of x, right, if this goes to 0, as n goes to infinity for each x in some interval I, then f of x is equal to what? Equal to f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2x squared plus dot 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 dot. Now, in terms of the language I've already introduced for you guys, what does that mean in words? What is that saying? So what this is saying is that, in other words, f of x, well, let me say it in other words. The Maclaurin series, if you like, since we're at 0, series for f of x converges to f of x. You're like, wait. Is there actually anything to worry about here? Is it even possible to have a function for which you can calculate the Taylor series and yet it does not reproduce the function? Is there such an example? In fact, there is. This is, to me, a far more subtle point than the second one. Trying to give you the big picture here before I get too lost in the details. The other thing we're going to talk about today is the issue of given a power series. In other words, something of the form a sub k times x minus c to the k power for given coefficients. What is its domain? See, that to me is a far simpler question. That question number 2 is of equal importance to us, though, and it's actually an easier question to address. But as a point of order in here, I do need to talk about the first question, at least for a little while with you. And that is, in fact, the whole reason for looking at Lagrange's formula for the remainder. Well, there's really 2 reasons to look at Lagrange's formula for the remainder. The one is to do estimation of error, as you just did in your homework, right? That's a good reason to look at it. It allows you to explicitly estimate error. That's cool. But the other thing is it allows you to actually, well, this gives us a tool to actually prove that a function really does have a Taylor series which converges to the function. By the way, functions that have this happen have a special name. We say f of x is quote-unquote real analytic on I. If a function is reproduced by its power series on the interval, then it is said to be analytic. All right, before I show you the counterexample, let's say, to this type of convergence in number 1, let's just look at something positive for a second here. So let's look at e to the x. That's pretty easy because, well, we'd like to show that e to the x is analytic. So and it's, in fact, it's analytic on the whole real numbers. The Taylor series I derived from you in my carefree, freewheeling style of the last couple of lectures without so much a care for the domain. That careless calculation we did, in fact, holds for all real numbers. Let's see why that's true. Okay, so what do I got to do? I need to calculate what is the you know, if I look at e to the x, I can do what? E to the x is equal to 1 plus x plus 1/2 x squared, right? Plus dot, 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 plus 1 over n factorial x to the n, plus the remainder, right? By what? By Taylor's theorem, right? So I'm using Taylor's theorem. Then what's my next move? My next move is to use Lagrange's formula for the remainder, which says what? By Lagrange's formula for remainder, what do we have? Rn of x is equal to what? What's the n plus 1th derivative of the exponential? It's e to the x. That's what makes this especially fun to think about. So this, you know, when you actually flesh out Lagrange's formula for the remainder for the exponential function, we just get e to the c, right, divided by n plus 1 factorial times x to the n plus 1. All right. Sometimes I get stuck here, right? But there's no reason to get stuck. What you got to do now is you got to think about, okay, what I need to do is I need to, where is C, by the way? If you draw a picture here. You know, okay, so like 0's in the middle, right? If this is x, the C is here. If this is x, the C is over here. I'm drawing two cases at once. I hope you can, I mean, do I need to draw separate pictures? Do you get the idea? All right, C is somewhere in there. So let's choose a particular interval to study. Let's think about, I mean, well, consider the interval I guess I can do, now here's where I'll get in trouble. I should probably follow the book. This is his example 3. So he looks at an interval J. So let's see here. So he says begin by fixing x and letting m be the maximum value of the exponential on the interval. So let's do that. Let's this picture wasn't wrong, but I mean maybe it's not helpful. So here J is going to either equal 0 to x, or J is going to equal x to 0, depending on if x is positive or if x is negative. All right. He says let m to be the maximum of e to the x, such that x is an element of J, right? I mean, what is it? It's either what? It's either, if x is positive, the maximum of the exponential is what? It's either m equals to what? E to the x for x greater than 0, or what? E to the 0 if x is less than 0. Right? The exponential, if x is negative, the exponential gets smaller in the left of the interval. It's largest at 0. So then, if you think about it, the absolute value of Rn of x is equal to is less than or equal to what? It's less than or equal to to m, well, yeah, fine. It's less than or equal to m times the absolute value of x to the n plus 1 over n plus 1 factorial. The point is that that exists, right? I mean, if you look at if you fix x, right, then there's certainly a largest and a smallest value the exponential takes going from 0 to x. Whether x is positive or negative, it matters not. Think of the x as being fixed here, right? What happens as n goes to infinity for that expression? What are you looking at? I mean, you guys have worked enough sequences to understand what happens here. You got factorial downstairs, right? Upstairs you have x to the n plus 1, but here x is just a fixed number. It doesn't matter what x is. X could be a billion. It doesn't really much matter. There's an n plus 1 factorial down here. It wins, right? Because you're looking at exponential. Well, not even exponential. This is like power. No, it's exponential. Fine, it's exponential, like 2 to the n or whatever. But it's exponential over factorial. We know that the factorial will dominate pretty fast, too. This goes to 0 as n goes to infinity, which shows, therefore, e to the x is analytic. It converges to its power series. Or rather, its power series converges to it, I should say. E to the x is analytic on 0 to x. Well, I mean, it's on j, right? But this implies analytic on the reals because j was just an arbitrary x, right? J went to an arbitrary x, so that's why, in fact, e to the x is matched by its power series everywhere. Excuse me. Now, if we actually tried to flesh out the details here, well, let me not say more. So what's the example? What's the cautionary example? Why does this even matter? If you look at this f of x, here's how it's, I mean, there's various ways of setting this thing up. I'll do it as follows. I'm going to say it's 0 for x less than or equal to 0. And it's e to the, I believe, minus 1 over x squared for x greater than 0. Let me draw you a graph of this thing. So it's 0, right? For x less than 0. Just like this. And then what happens at 0? It becomes non-zero, right? To the right of 0. How about its derivatives? So like, what's f prime of x equal to? And let's suppose x is positive. You can differentiate it, right? You have e to the minus 1 over x squared times what? Chain rule, right? Minus 2 over x cubed. Is that right? Did I do that right? Hmm? So it's x to the power minus 2. That's the inside function. So the derivative is minus 2, x to the power minus 3. In other words, minus 2 over x cubed. Let me clean this up a little bit. You've got minus 2 e to the minus 1 over x squared divided by x cubed. What happens to this as you approach 0 from the right? I won't go through the details, but you can show that this goes to 0 as x goes to 0 from the right. I mean, it's what? That has form. Well, at the moment it's indeterminate, right? Because that's e to the minus infinity, which is 0, right? And downstairs I've got 0. This is type 0 over 0. You got to do L'Hopital's. something like that in order to resolve the indeterminacy. But trust me, you can show that this is going to 0. And in other words, and of course the derivative, that's the right derivative, right? The left derivative, well, the left derivative is 0 because it's the constant function 0. I don't need any fancy schmancy analysis to figure that out, right? The derivative from the left is clearly 0. So what that says is that f prime of 0 is equal to 0. So this function looks something like this. What is it asymptotically going to? What's this value? It's 1, right? As x goes out and out here, you get e to the, oh wait a minute. Well, that's not right. Let me think about it for a second. What happens e to the minus 1 over x squared as x gets really big? It's like e to the, oh yeah, it's e to the 0, right? Which is what? 1. Okay, so yeah, my graph is decent. Now, here's the thing. It turns out, and I'm not going to spend a bunch of class time to show you this, but it turns out that f prime prime of 0 is also equal to 0. And in fact, the nth derivative at 0 is equal to 0. So, what is the Taylor series generated by f in this case? I very much believe this example should not be relegated to exercises. It's important for this to be in the body of the text. If this isn't in the body of the text, I think it's really hard to appreciate what's the point of talking about this whole issue. I mean, yes, there's the approximation like I had in your homework, but there's another deeper reason, which is I'm trying to explain to you right now. So, the Taylor series for e to the x at c equals to 0, in other words, the Maclaurin series is what? 0 plus 0 plus 0 plus 0 plus dot, dot, dot. It is identically the 0 function. If I graph the Taylor series generated by this function at 0, it's this green line down here, right? As you can see, the green line and the red line do not match, right? That's because this is an example. This is, in fact, the quintessential example of a function. This function is what's known as smooth at 0, but not analytic at 0. Now, when I say analytic at 0, what I mean is there doesn't exist a neighborhood of 0 on which it's analytic. Doesn't matter how far you zoom in, if you have to the left and to the right of 0, you cannot match this function with its Taylor series. You would not be able to show that the remainder goes to 0 for this function if you tried to do it. Okay? Listen, I don't really test much on this because it's really difficult I personally find this somewhat challenging, this argument. All right? And this is pretty much the simplest example you could think of. The only thing maybe simpler than this, maybe I could ask sine or cosine. If the stars aligned correctly or whatever, if you believe in that sort of thing. I personally don't. But, maybe you could find a way to ask a question about this. But this is really subtle, this issue. And so I need to tell you about it because I think it's important conceptually to be aware of the issue. But that's about all I have to say about it. The way I would probably test on Lagrange's formula to the remainder, if you'll allow me this annoying and unnecessary comment about how I test on things, would probably just be like on your homework, right, where we use the remainder formula to estimate the error, right? That's a more sort of straightforward path on how to understand Lagrange's formula for the remainder to do something practical and that we can all understand. I owe you a proof of something, of course, and that is what? What did I not explain at all yet? Man, the buttons in here don't work. Oh, it's still not working. It didn't work yesterday, it still didn't work. I guess I've got to unplug this thing and start over, but I don't want to wait, so I will use my workaround from yesterday. I still owe you guys a link to this. I'm sorry I haven't gotten to it yet. Lately, semester has been very bad for me. Go away. Ah, not like that. That was not the kind of going away I wanted. Oh man. Come on. I think I was looking at old school calculus 2 view full screen mode. Haha. All right, come on. We are in close to there. Here it is. Here's Lagrange's formula. Taylor's theorem with Lagrange's formula for the remainder. Here's a statement of it. In my notes, it's theorem 6.5.6. So it's almost the same thing we were looking at so far today in class. The difference is rather than calling one of the endpoints x and the other one 0, I call the endpoints a and b. So to translate between what we were just looking at in section 12.6 in my notes, maybe you should set a equals to 0 and b equals to x. All right? That's pretty much it. And then we have, the Lagrange's from the remainder. So here's the proof. The book does not have a proof. The book relegates the proof to an exercise, which is fine. But here's the proof. I'll try not to spend too much time on this. I think it's good to see it, but I don't think we need to belabor it either. If I could find my laser, it would be better. Oh no, I have lost my laser. Oh, I think I left it at home. My kids were playing with it. All right, so this will have to do. So first of all, you've got this function, right? And it's differentiable. So you can look at the value a and the value b, these are given, and you can define this m implicitly by this equation. If you want, I could solve this equation for m and say m equals blah. Okay, same thing, all right? Nothing mysterious here, this is m. Then what you do is you define another function g, which is basically putting this thing to be 0, okay? It's basically setting this equal to 0. So g of t is, and replacing the a with a t. So you have g of t is minus f of b plus f of t plus f prime of t, b minus t, dot, 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 dot. Everywhere there was an a, I replaced with t, and there's the m, all right? Now, what makes this g interesting is it satisfies Rolle's theorem. If you look at the interval that has endpoints a and b, it's either a, b, or ba, depending on which one is less than the other. So like, check it out. If you plug in t t equals to a, what happens? You get, yeah. Let's see here. Put an a here. This is b minus a, b minus a. This is, well, look up here. If you put t equals to a, if you go back up to here, you can see that it should be 0, right? So to see why the g of a is 0, compare this and this. Think about what it means. When a is equal to 0, that's 0 by the definition of m. Yep. Construction, I did it. The reason I'm doing it is basically I'm moving this to the other side. You may remember the proof of the mean value theorem from last semester. We do something similar. We take the equation for the secant line and we move another term to the other side so we can apply Rolle's theorem to it. It's essentially the same step, except instead of doing it for the secant line approximation, we're doing it for like the polynomial generalization of that. Now, if you plug in b, well, it's just straight 0, right? So you have this function g, which is 0 at a, it's 0 at b, and next I will show that in fact it's differentiable between a and b. That means I can apply Rolle's theorem to find a c between a and b for which g prime of c is 0. All right, so to show it's differentiable, I guess it's kind of already clear from the formula it's differentiable, but here's actually the differentiation of it. It's kind of a mess. But after a little bit of work, you come to this formula, b minus t to the k minus 1 over k minus 1 factorial, the kth derivative of t minus m. So that has to be 0, but you can argue that this front factor is non-zero, so that forces this to be 0, which means that there is some c between a and b such that f, the kth power, f upper k of c is equal to m. If that has to be 0, that has to be the case. And that's exactly what you want for Lagrange's formula of the remainder, that there exists some c that you can plug into the next derivative that you're not using in your Taylor polynomial, and that will totally like encompass the remainder. My personal intuition for this is somewhat related to the theorem of Carr-Theodori, Calculus 1, but you probably haven't seen that unless you had Calc 1 with me, so I'll shut up about that, since I don't think any of you had Calc 1 with me. If you did, that means you didn't pass my class, right? So I haven't taught Calc 1 recently. So yeah, I don't think that was the case. Anyway, there's the proof. That's the error. He's relegated that to an exercise. Did I assign that exercise? I don't think I did, right? I would have gotten questions about that exercise. I'm pretty sure. That's a doozy. All right, so there's your proof. And with that, I will go on to the much, much easier question of number 2. So I guess if you had to describe my lecture style, you might say it's Machiavellian. I like to do my evil all at once, you know? So that's kind of what today is, right? Not entirely true. I'm not going to prove anything much about this. I'm just going to tell you how it works, all right? So the proof of these things will have to come another day. We don't have enough time to do it properly. But I just want to tell you what happens. What is the possible domains for a power series? Let's look at some examples. You're like, how can you figure out the domain of a power series? Let's start out with what we were just studying. How about e to the x? Oh, forget e to the x. Let's look at how about sine of x? I claim that was equal to the sum k equals 0 to infinity, minus 1 to the k over 2k plus 1 factorial x to the 2k plus 1. Admittedly, I'm just glossing over what? Can you forgive me for that? If I don't talk about it, I won't ask it of you. How about that? Can we agree? Or would you like, if you want to go there, we can go there. We can start doing this for all of the examples. Try to understand. I mean, that's the next level of analysis, but I think that you guys have more than enough to do at the lower level, so let's stay there. All right? There is a subtle question to address. Does that really converge to, is this equality valid? It is. Sine is also analytic on the whole reals, as is cosine, cosh, and sinh. Okay, but forget that this is sine x for a second, all right? Let's just call this thing this. I don't know, what do you want to call it? Let's call it S of x. It's a series, power series defined at x. And how could you figure out what's the, what x this converges for? How do you analyze whether a series converges or diverges? What's your go-to tool for some formula like that? What would you use? Ratio test, yes. Ratio test is our go-to for these examples. So we want to look at and we can look at the absolute value of it, right? So 1 over, sorry, I'll eventually make up my mind. Let's call this whole thing a sub k. So what I want to do is I want to look at the absolute value of a sub k plus 1 divided by the absolute value of a sub k, which is what? The minus 1 to the k goes away. What are we left with? Absolute value of x to the 2 times k plus 1 divided by 2 times k plus 1 factorial divided by, let's see, 2k plus 1. Why didn't I should have stuck with that exponential example. That would have been easier for me to write. Oh well. All right, how does this, yes, sir?
Would you put like x to k plus 1 plus 1? Why is k plus 1?
Because I want to remember not to forget to multiply it out like I'm supposed to. Because when I simplify this, I have the absolute value of x to the 2k plus 2 plus 1 plus 3. And upstairs, I, of course, have 2k plus 1 factorial. Downstairs, I've got 2k plus 3 factorial, absolute value of x to the 2k plus 1, using properties of absolute value to pull things out, right? The point is I want to make sure I don't forget to distribute the 2 multiplying the 1, right? I'm looking at a sub k plus 1, so the k is multiplied by 2, so I have to put k plus 1 in the place of k. Yeah. But this simplifies, right? What is this? This is just, check it out. It's just the absolute value of x squared divided by what? 2k plus 3. 2k plus what? 2k plus 2, right? And the 2k plus 1 factorial cancels. Do you guys follow me without me writing it? Do you know the cancellation I'm referring to? It's just like a problem we did the other day, right? X is independent of k, right? X is a real number. Could be any real number. Could be a billion. Could be minus. Could be minus Donald Trump's net worth. I don't know. Whatever. The point is, it doesn't matter what x is. If it's fixed, independent of k, as k goes to infinity, this goes to what? 0. Thus, the absolute value series, in other words, the sum of the absolute value of a sub k, converges for S of x independent of x. So what's the domain of S of x then? It's the whole deal. Yes, sir? Yeah. It's okay. I mean, that's the thing I skipped. This, by the way, is called the interval of convergence. The domain of a power series has a special name. This is the so-called interval of convergence. Now, I personally get tired of writing interval of convergence, so I will shortly start abbreviating this by IOC, and you are allowed to do the same. And the radius of convergence sometimes also known as what? The ROC. I also call it big R. That's equal to infinity here. Let's see here. Another example. If I have the sum, x to the n equals 0. Well, I guess I've been using k. Fine. K equals 0 to infinity of x to the k, right? What's the interval of convergence for this series? Find the IOC. So what do? We look at the ratio of absolute value of x to the k plus 1 over absolute value of x to the k, right? By the way, what was I using up here? What does this give me? This actually tells me what? This actually tells me absolute convergence, right? I'm using the result, the absolute convergence implies convergence, right? I should mention that. And I'm going to do that again here. If we look at if we apply the ratio test to the absolute value of the power series, right, we will get proof of the absolute convergence of the power series for certain x. How's that? This is easier, right? So that's right, which is what? X. See, the ratio test came out to a ratio which is not independent of x this time. When does the ratio test work then? It has to have this less than 1, right? Which implies that minus 1 to 1 is a subset of the IOC. I can't conclude from this that minus 1 to 1 included is equal to the interval of convergence. The ratio test, what it'll tell me about is the open interval of convergence. It tells me about everything up to the endpoints. So what we'll see as we further this discussion tomorrow is that to ascertain whether the endpoints converge or not, you have to test those separately using other things like alternating series test or p-series or whatever. But the ratio test will give us absolute convergence on the open interior of the interval of convergence. And in fact, this is almost everything that can happen. It turns out that the domain of a power series, it's either the whole real line or it's an interval, a finite interval that's either closed or open or half closed or half open. And then there's one other case, the case I mentioned at the very start of this. The domain could just be the single point, the center of the series. That's the other case. But that's it. That's all that's possible for the domain of a power series. Isn't that simple? I mean, it's not, you might not see it as simple yet, but I mean, when you think about all that's possible for domains of functions, the domains of power series are really, really quite boring. But I'll shut up there. Thanks, guys. Oh, quiz. Oh, I'll send you the quiz, let you do it at home. How about that? Would that be better? Yeah.